think we can start. So welcome to this session, the first parallel session in this room for today. I'm Antonio Padovano from the University of Calabria. I'm going to chair this session entitled Automated Factory and Collaborative Robots in Industry and Logistics. And I would like to welcome the first speaker, Rudolf Pichler, who is going to present the paper Enhanced Agility for Assembly Tasks via Self-Sufficient Mobile Working Station. So please, Rudolf, the stage is yours.
Thank you. You can hear me all quite well?
Yeah, perfect.
Yes, wonderful. Yes, welcome to my speech. As already mentioned, Enhanced Agility for Assembly Tasks via Self-Sufficient or Autark Mobile Working Stations. My name is Rudolf Pichler. I'm Senior Scientist at Graz University of Technology, and I'm the head of the so-called Smart Factory at TU Graz. This is a research and learning factory like we have got a couple of in Austria, and I'm very proud to present you our first scientific outcomes of this learning factory and what we established so far. My agenda is about the following. I will tell you some words about agility. Agility, I say and I state, has arrived at the shop floor. I will tell you something about the characteristics of mobile working stations like we did it here in our learning factory. I will tell you about the actual progress in the build-up of an agile infrastructure in a shop floor. And last but not least, I will end up with future topics in research, what we are doing in concerns of production-related agility. Let's go into the word agility. We know a lot of buzzwords around in the world of production, and I want to warm up with some statements. Of course, agility, as we know so far, is best known from, and it was developed in the software environment. But in the meantime, agility has become a company-wide philosophy. And I always tell my students, please do not mix up agility with flexibility. And a short description or a short determination is agility is more than flexibility because it's proactive. It is able to open and to be ready for new markets. It is a kind of readiness for doing new products and new processes. And this could make even more profit than only to be flexible, what is, in my opinion, only a fulfillment of a certain line of orders, but not more. So if we talk about agility in the world of production, it shouldn't remain with these simple statements, but the answer we took into our research is what now about agility? What does it look like in a shop floor, and how could we live agility? And the wonderful thing is that we have a very small model factory, the smart factory, and we already could do physical things and not only to remain in PowerPoint presentations and producing theoretical papers. So my answer, our first answers, how can agility be executed pragmatically, is the following, or the first characteristics we took into concern. We said, let us design or let's do the design of single facilities of a process, and let's do it with standardized modules. And this is pictured like here, as you can see, means we have a certain line of assembly, preferably already existing or one for the future, but have it split up into modules to handle it very more easily than with stiff and hard automated assembly lines. Then as a next imperative, we said, build these modules movable, and let's have done it with universal platforms and interfaces to be, again, not only flexible, but agile. We want to have we want to prepare and to be ready for quick reconfigurations, to be ready for new alignments of these modules, means to be ready for doing new processes and producing new products. And last but not least, for being this agile, it should also be the fact that we want to avoid any physical connection to the ground or to the wall of our production, of our shop floor, because this would mean in the course of reconfiguration, it would block and hinder us. We have to do the unwiring and the rewiring, and this could make a couple of troubles. And in the end, being agile also means to be fast, yes? And this avoidance of connections should make us do easy isolations, means to split up of an existing line and to do an easy reintegration of these modules. And then it should be able, just as a symbol or as a picture, it should be ready to have split up the old line into some new line and to new process for making new products the market needs very quickly. So this is an insight or a view onto our smart factory. And here on this example, I want to show you how what we did and how far we came. And what you can see here is this modular concept. We call it all these as mobile working stations, and the characteristic of these mobile working stations is described later on. But what you can see here, this is single modules easily to be taken out or to brought into a new alignment of the flow for a new product. One important thing is that we are ready or wanted to be ready not only for translatoric movement, but also for a rotatoric new use of these mobile working stations. This meant as construction principles, we took the following. We said we need standardized dimensions because the alignment shouldn't be a very wild puzzle, but it should be the dimensions of these squares. For example, in our case, it's 700 millimeters by 700 times 700 millimeters, or in this case, it is 700 times 1,400, means the double. Yes, this plate, as you can see here, it is the double of two single plates like here. Of course, we want to have it movable, simply means we So sorry for this, ladies and gentlemen, you can hear me again?
Yeah, now we can hear you.
So we have to go back. What was the last? I will share once more. So you can hear, you can see my slides again. What was the last slide, or what was my last statements? You still could hear?
Yeah, it was quite here.
It was quite here. Okay. So the connection still is working again.
Fine, yes.
Okay. Sorry for this. Normally, I haven't got these problems. So the main characteristic out of a couple of is, and this is what I want to point out, and it is in the headline, is the self-sufficiency or the autarky of these mobile working stations, as you can see in here, and I will go into it a little bit deeper. So this autarky or self-sufficiency is done in many ways. First of all, because I don't want to have any wires or cabling, and this is why we did the power supply, the electric power supply, via an accumulator. This is a unit with the current output of 24 volts, but we have also a transformer because sometimes we need a robot on top of this mobile working stations, and this robot needs 240 volts. Then we have an additional transformer. But other electronic devices and PLCs we also have got underneath this table. They are fed with these 24 volts. So means we don't need any cabling or any wire to these mobile working stations. Additionally, we have some applications that need some, like you can see here, maybe this is a pneumatic press, and pneumatic presses, of course, need compressed air. And again, here we followed the way, remain self-sufficient, and here you can see the tanks put underneath these tables. And so also here we don't need any hose coming from the ceiling or coming from the walls or from the ground or elsewhere. And last but not least, not only the power supply, of course, in a smart factory we need a lot of information, and this is the more easy part, one could say, but the information transfer to all these units is coming from the ceiling via a router placed here. The whole information flow is coming down from a manufacturing execution system. It's going to a brain, this is an industrial PC, and wireless, the information is brought down to the sub-PLCs of the single working stations, and then the aggregates, the robots, the presses, whatever, they can cooperate. And this is a very nice, but also very complicated things, because you have to follow one standard. Mainly we did the PLCs with Siemens. This made it a little bit easier because each working station, as you can see, is equipped with Siemens PLC, like you can see here, or you can see here. But we also would be ready to work with different PLCs, what would need additional middleware for getting a common information. All in all, the smart factory is also collecting process data, and we are sending it back via the router to and do the upload into the cloud for having data executions or doing big data applications. So this is also the being self-sufficient of the information flow. And once more, I want to point out that the self-sufficiency of our mobile working stations is the major enabler for a quick and easy reconfiguration of any assembly line. So let's go on. What else do we have for being agile in our smart factory? Or if we work with agility, how can we bring this along? First of all, of course, we have to do, when a new product or a new process should be established, we need a feasibility check. And what would I say is a feasibility check? There is the certain demand of technologies deriving from the product that is demanded and required, and this has to meet, of course, the availability of technologies, in our case, put and executed via the mobile working stations. We're doing it quite manually so far, means we have lists of capabilities, what the single mobile working stations, for example, here the handling, with or without the robot, with certain grippers, power supply, whatever. We have a mobile working station that is called screwing and pressing. We have a couple of skills, as we say, and we have to compare with the requirements and the demands coming out from a new product or a new process. And then we can say there's typical results. The feasibility is either fully given, feasibility is given with necessary adaptations. Mostly this is the case, or it is too hard, feasibility is not given. At this stage of our research and when establishing it, we are still on the stage that we have to do this manually, and this is of course not very satisfying. Sooner or later, and our research is heading for a solution, of course, that we have an automated comparison. The thing is, being agile as a company means to give your customer a very quick response if you can do it, in which time, if you can do it either, and at which conditions. And that is why this feasibility check, of course, should be automated, or let's even say semi-automated. What else do we use, or did we install for being able to do reconfigurations rather easily or even supported? If we start with, we have the single mobile working station here. We equipped all the mobile working stations with transponders. Transponders, this is active transponders, means they carry a battery inside here, and they are able to give our system. The whole factory is equipped with 9 anchors or gateways, and on the ultra-wideband based communication or radio technology, it is possible to see where are our mobile working stations located. And once more, to point out, why do we have 2 of these transponders on the opposite edge? Because we do not only want to know, for example, here, what is the translatoric position of these mobile working stations, but also the rotatory position. And this should help us to locate, or even for having a new definition of a new arrangement, a new alignment, where to bring it. To be honest, this system is still, in my opinion, rather poor, because the accuracy is not better than 20 to 25 centimeters. And if you can remember the picture before, we have one robot here on this maybe working stations and a robot on the second, and they must cooperate. Then it's quite clear that this accuracy is not sufficient enough. What we are doing is that we have an additional system to be for getting more precision, and this is the need and the use of image recognition, and this is still in progress. This work is still in progress. So, why is the position or the new position of these mobile working stations necessary? Of course, we work with AGVs, autonomous guided vehicles, and they must directly and very precisely find the new position, because they are the carriers to have one semi-product, bring it to the next station. If not, the part itself is forwarded by the robot itself to the next station. This is one element and one part of the whole system, and of course we need even more precision. So nevertheless, we started with it. The RTLS, the real-time locating system, is useful for, once more, to detect the actual position of an mobile working station. It provides the actual address of any source of any mobile working stations for the AGVs. And sooner or later, I will show you in the next slides, it is a research topic that we are heading for, an automated reconfiguration. This just for the equipment so far we have got in our learning factory. So, and right here we are in the ongoing research topics. As mentioned before, we would need this position very precisely, because what we try to find out, how could it work that such a reorganization isn't be done by humans or workers alone, but maybe we could do some work already overnight, because time is money and we have to prepare and bring out the new product very, very soon. And for this automated reorganization, there's one idea I want to introduce at this stage. It is the following. We have to replace this unit according a certain plan that has to be developed and planned before, and we want to do it with very flat HEVs and vehicles that go underneath these units. Of course, there's still a problem. The rollers are locked. Yes, this is one problem. I haven't got the solution so far. We have to solve this different. Maybe we have to do it without rollers in any case, because the rollers are only helpful for a manual change. If we do it with this unit, we don't need rollers at all. So, and as soon as this unit goes underneath these mobile working stations, of course, we must lift this unit. And then, according to a certain program, we can reorganize or replace this unit in a, maybe at first hand, a very rough, but at a first stage. Of course, I want to point out with the next, there's a lot of vehicles like this, and we still have to find out. Our actual problem is to find one very flat unit that goes underneath, and it must carry quite a heavy load. This unit with a robot on it comes up to 100 and even more kilograms, and this is not very easy, because also this unit has to carry a battery, and yes, the solution is not right in front of us. Yes. So if we want to do this automated reorganization, there is a couple of questions still. What we first do is, of course, to foresee all the mechanical preconditions to have this system worked. Then we have to do a lot of work on the software programming, because we have to create a program for the reorganization, execution. For example, what is the sequence? First, we need a plan. What does it look like, the new alignment? And then what is the procedure? What is step one to the final step? Because we must tell these vehicles what to do. And sooner or later, we do this in cooperation, of course, again with the RTLS. And this, as already mentioned before, is not sufficient. We also have to integrate software and means of image recognition. This is a really big journey, and nevertheless, what I think is that maybe this is not free and fully automated. We still, I think, need the humans, even at this stage of our research, because to complete this reorganization, we have to think about that the calibration for precise interaction is necessary. As mentioned before, it is really very important if there's cooperation from the setups from one mobile working stations to the next. You need millimeters and even fractions of millimeters. The placement of the new placement of these working units has to be very, very precise. And in my opinion, we still need the professional worker. And last but not least, it is also, there have to be a couple of adaptations in terms of safety, because it looks all very freely accessible. Of course, there have to be also new conditions in the safety precautions. So, and as a next or one more research topics, as you could see, all this technical equipment is quite costly, and of course we have different levels of automation we can do for being agile, but nevertheless we have to take care that we have to prove if all these investments really pay off, and so one has to be aware that such an automation, a full automation of such a system is quite complex and risky in terms of technical and financial terms. And last but not least, it is quite evident for a company that a sound balance of this investment compared with the benefit has to be found. Means, as for we are also at our university and our institute, we are also regarding the economic aspects. This will still be a future. Which level makes sense, and at which stage or which level we run into really high or too high risks. We have to give answers for industry also in this concern, I think. So this was a short insight what we have already built up and what we are heading for. And so let me do a summary once more. I definitely would say agility at the shop floor is not a buzzword anymore. There is, not only by us, there is already solutions. And the wonderful thing is that we've got a physical execution and a test field for future ideas in our learning factory. That mobile working stations, as one answer, allow to provide really quick responses for new markets. The major issue, a major key for having success is self-sufficiency of these mobile working stations. I demonstrated in a couple of power supplies and other supplies the degree of automation for the reorganization of the fleet because we have not got only one or two, but many more mobile working stations. The degree could, of course, be endless. Especially we researchers always have good ideas, good and sometimes very costly ideas. And last but not least, the economy of any automated agility concept is limiting excessive ideas very soon. Yes, and once more, we have to find the balance. Otherwise, maybe industry would say, really great, but in a way you are dreamers, and this is not what we want and intend. So, ladies and gentlemen, this was my short speech and the insight what we are doing in concerns of agility in our learning factory. And so I thank you for your attention, and I'm ready for your questions.
Thank you, Rudolf, for your very interesting speech. Is there any question? You can raise your hand. I actually have just a very quick question. Oh, we have a question from Patrick. Patrick, please.
You're right. Thanks a lot for the talk. I have a question regarding what is the benefit of bringing let's say the factory to the product instead of the product to the factory, or to the manufacturing tool?
What is the benefit to bring the product to the factory?
Yes.
Instead of bringing the factory to the product?
Yes. And what I mean here is the place where it is produced is now rearranged, right? But how about having the same module every time at the same spot and bring the product to the right place? What I mean is that the product finds a way through the production itself.
Maybe I did not really understand your question. What we always know is where is the facility standing around, especially for an HEV. Yes. Mm-hmm. Maybe we are not on the same page what agility means. Agility means, or what I introduced to you is you're producing gears or a certain type of product, and suddenly you have the big chance. I always tell the students there's the big chance to produce a quite similar product, but it's not in your product program. But you have the facilities for it, and of course you have to arrange or rearrange your production lines. In this case, of course, assembly lines. And how could you manage this very, very quickly? So that is why I do not really understand the product comes to factory or factory comes to product.
Oh no, it was just the rearrangement. Does it make sense to rearrange the whole factory instead let the product go through the factory itself? Okay. But I think it was answered already, kind of.
Maybe one addition from my side. What we learned is where do you lose time? We are on the same page that time is the most important fact for consumers nowadays. Just think about the online trade. Yes, you press on the button, then you want to have it in the next hours on your table. Yes, and to produce a new product, you do machining, you do assembling, a lot of things is of course much more work than picking it out from some warehouse somewhere in Europe with a super parcel service. So we must be very quick. The next is, where do we lose time in a manufacturing, in a shop floor? It's always the logistics. If you do not, this is my opinion, if you do not rearrange your facilities and your machinery, the smaller machineries, then you have a really bad logistics. And this leads to errors, this leads to time faults and much more. But it is an interesting question. And again, when does it still make sense, and doesn't it cost too much, and when not? I hope I could answer your question.
Yes, thanks a lot.
Satisfying.
Thank you, Patrick, for the question. Thank you, Rudolf. I have just a very quick question for you, Rudolf, because as you said at the beginning and at the end of your presentation, agility is much more than process flexibility.
Flexibility, yes.
So the modular architecture of Smart Factory that you have presented is extremely powerful to reconfigure quickly assembly processes. But agility is much more. I mean, is about even getting closer to the final customer, providing like manufacturing as a service paradigm. So
for example, yes.
For this reason, in this sense, manufacturing execution systems, MES or ERP, play a relevant role and must be integrated with this modular architecture. So my question is, where this self-sufficient mobile workstation that you were presenting already integrated with business level software to enable this agility, or maybe is it just a future step of your research?
Okay, what I didn't mention because time was not enough, we also have not the shop floor, as you could see in this picture. On top we have the IT level with a PLM system, product lifecycle management system. We've got an ERP system, and we have got a manufacturing execution system. Of course, these the IT level also must be agile, or must be ready for agile. And this we still can check and prove in our smart factory. But I'm fully agree with you. These systems must be agile as well. And what we are really taking care about is that we have a seamless data integration. For example, we have one showcase in our smart factory that we have already we did an order for the machine tool to produce a part, and suddenly we say the customer calls in and says, I need not 5 drills, but or windings, but I need 4 windings in a certain part. And then we show that with the integration of data, we can show that within 5 minutes, including an FEM check, we can bring out at the machine the correct or the corrected part the customer desired.
Thank you.
We call it late customer integration. But I'm fully agreeing with you that it cannot. The whole company must be agile in the end. But normally there's no answers or only little answers what the shop floor can do for it, and this is one possible answer.
Yeah, thank you very much, Rudolf. Okay, so thank you again for your speech, and let's move fast to the second speaker, who is Alexander Kinast. So Alexander, please feel free to share your screen, and he's going to present a paper entitled "Biased Random Key Genetic Algorithm for COBOT Assignment in an Assembly-Disassembly Job Shop Scheduling Problem." Please, Alexander.
Thank you for your introduction, and welcome to my presentation, Biased Random Key Genetic Algorithm for the COBOT Assignment in an Assembly-Disassembly Job Shop Scheduling Problem. My name is Alexander Kinast, and I'm currently a PhD student at the University of Vienna. I created this paper with my 2 supervisors, Karl Doerner and Stefanie Rinderle-Ma. So what will be the agenda for today? I will start with an introduction of the topic, where I explain the basics of a job shop scheduling problem and why cobots are used in production. The second part will be the problem description, where the problem and the general objective function is described. In the third part, I will talk about the solution method. This includes how existing methods are adapted. The fourth chapter will be about a real-world dataset that we use to test our developed methods. In the last part, I will talk about preliminary results that we have achieved with our algorithm on the real-world dataset. So let us start with the introduction. In a simple job-shop shadowing problem, jobs, tasks, and machines are given. Jobs group together tasks logically. This can be seen at the top of the picture. An example job would be a production of a motor. To produce a motor, many logical tasks must be done. For the tasks, we already know a deterministic production time. In a simple version, tasks can be produced on all workstations and an available time for all workstations exists. The optimization goal for such a job-shop scheduling problem could now be to minimize the make span. The make span is the time until all tasks have been finished. This can be seen at the bottom of the picture here. So if you have some jobs that have tasks in it, like here the job 1 has 2 tasks and the job 2 has also 2 tasks, and we have 2 machines with an available time, then the jobs or the tasks are assigned to machines, and the make span is the time when all tasks finished producing. Okay, let us head over to the explanation of the cooperative robots. A cooperative robot has the abbreviation COBOT. The difference to fully automatic industrial robots is that cobots can share a workspace with a human actor. However, because they share a workstation with a human, they move slower than industrial robots. Cobots can do work either on their own or in cooperation with a human. So typical industrial robots are used if the work allows a high degree of automation. Cobots can be used on workstations where 20 to 40% of the work can be automated. And it is assumed that the cobot increases the speed of a workstation by 30%. According to the producers, they can be set up on a workstation within half a day. So they are pretty fast to set up. On the right side, a typical cooperative workstation can be seen. There, the human worker places a screw on a mechanical part, and the cobot screws them in. So here, the human and the cobot interact with each other on the workplace. Cobots can additionally be used to reduce the amount of unergonomic and harmful tasks a human worker has to execute. An example would be a battery end-of-life disassembly. When a battery is disassembled, the cobot can do tasks where the human might have contact to hazardous substances. Additionally, cobots can do tasks like pick and place, screw driving, and injection molding, and many more. On the right side, a picture of a real-world production workspace can be seen. This picture is from the car manufacturer BMW from the location in Dingolfing. So let's head over to the problem description. The general settings are similar to the simple job-shop scheduling problem with some extensions. In these settings, orders have tasks that need preceding tasks to finish before they can start. This can be seen at the top of the picture. Also, workstations are grouped logically. For example, screwing or assembling tasks can be done on all workstations of such a group. This can be seen in the center of the picture. So here the machines are grouped. However, workstations can have different costs and production speed. This might be due to newer or older machines, but can also be due to more or less workers. For this problem, an ideal environment with no uncertainties and therefore a fixed production time is assumed. So additionally, the amount of cobots is limited. This means that cobots should be placed on workstations where the highest improvement of the target function can be reached. This might be workstations with high costs or workstations that delay the rest of the production. In most companies, the orders for the next planning period are already known. It is assumed that cobots are fast to set up. The tactical cobot to workstation assignment can be mixed with the operational task to workstation assignment problem. So now let us head over to the objective function. To optimize a job-shop scheduling problem, various objective functions can be used. An example would be to minimize the production cost, no matter how long the production takes. This would result in a solution where only workstations with the lowest cost in a group are used. On the other side, if the make span should be minimized, fast workstations will be used a lot, no matter how much it costs or how much time is left. So in a real-world application, often weighted objective functions are used. A general objective function could be alpha times production cost plus beta times make span. So let's head over to the solution method. I will first explain a genetic algorithm. The chop-chop scheduling problem is an NP hard problem. This means that large instances cannot be solved exact in reasonable time. Different heuristics, such as a genetic algorithm, have been applied successfully on these chop-chop scheduling problems to find nearly optimal solutions in reasonable time. A genetic algorithm is inspired by natural reproduction and has the following steps. First, a population is initialized with random solutions. The next step is a fitness assignment, where a fitness value is assigned to each individual in the population. With this fitness value assigned, the parents for the next generation are selected. This is called selection. In the next step, the crossover step, new children are created out of the selected parents. After creating the new children, they are mutated with a given probability. The mutation is used to reintroduce genetic information if important genetic information has been lost. And at the end, we have a stopping criterion, like a target fitness, a maximum generation amount, or a given runtime. So the algorithm will stop if one of the stopping criterions has been reached. Otherwise, the algorithm will continue with the next cycle at the fitness evaluation here. So now let us check out the problem encoding. In the integer encoding, each task is encoded with two values. The first value encodes the workstation where the task is produced. This means if a task can be produced on workstations 1 to 3, only values in this range are generated. This can be seen here in the gray fields of the workstation of the encoding. The second value encodes the priority of a task. If multiple tasks can be produced at the same time, the task with the highest priority, where all preceding tasks have been finished, gets produced first. This can be seen in the yellow fields of the picture. These are the fields here. So for one task, we have a workstation and a priority encoded. For each COBOT that should be assigned to a workstation, an additional integer for the workstation is encoded. This is the red value at the end of the picture. So for example, if we have 50 COBOTs, 50 workstations, and we have one COBOT to assign, this value describes that on workstation 25 a COBOT should be placed. Since all values in these encodings are integers, all operators that work with integer arrays can be used to solve this problem. So the second encoding is the biased random key encoding. The biased random key encoding is similar to the integer encoding with some key differences. Here are all values encoded as floating point values between 0 and 1. This value then gets matched to the corresponding workstation. For example, if two workstations are available, the first workstation is used if the value is larger than 0 and lower than 0.5. The second workstation is used if the value is higher than 0.5. This means that the bounds of the encoding are not influenced by the number of workstations available on a workstation group. So here, always a value between 0 and 1 is generated, no matter how many options we have for the workstations. In the picture we can see, so the value in yellow again represents the priority. So like here we also have a value between 0 and 1. And in red we can see the COBOT to workstation assignment. For example, if 50 workstations are available, each workstation has a range of 0.02. This means the red value of 0.05 would mean that the COBOT is assigned to workstation 3. Since all values in this encoding are double values, all operators that work with double arrays can be used to solve this problem. So let us head over to the real-world data. To test the new encoding and to influence of COBOTs on the solution quality, a real-world dataset was used. The real-world data consists of 210 orders that group together 1,265 tasks. Each task can have a preceding task that have to be finished before the production of this task can start. A task typically has either a workstation given, where it should be produced, or a workstation group where the workstation can be decided. For each of the 54 workstations, costs and speed factors exist that modify the production time and the production cost. To increase the complexity of the dataset, it is assumed that tasks where a workstation is given can be reproduced on all workstations of this workstation group. So let us head over to the preliminary results that was achieved with the new encoding. For the production, 5 cobots could be assigned to workstations. By using a simple rule-based approach, we found out that the production cost was around 5 times as high as the make span. To factor in both values equally, the general objective function from slide 10 was adapted as production cost plus 5 times the make span. The genetic algorithm had 5% mutation rate with 1 elite per generation, and each generation consisted out of 100 individuals. To test the encodings with comparable settings, operators that can be used on both encodings were used. To select the parents, a fitness proportional selection was used. As the name says, the chance for an individual to become a parent for the next generation is proportional to its fitness. This means fitter individuals have a higher chance of mating. In the uniform sum positions arithmetic crossover, each position of the parents has a chance to be crossed. The manipulator that is used is an all positions manipulator. This manipulator influences all positions of the vector with a given strength. For the integer encoding, the rounded version of the mutator and the crossover is used. So to increase the amount of datasets where we can run our algorithm, the tasks are split. This means I1 are all tasks, I2 is the first half of the task, and I3 is the second half of the tasks, and I4 to I7 stand for the 4 quarters of all tasks. So now let us look at the calculation time for the different datasets. So in the table, the calculation time of the optimization runs can be seen. All calculations are performed on an Intel i7-8700 CPU. On the vertical axis, the calculation time in minutes is displayed. On the horizontal axis, the dataset can be seen. As described on the previous page, I1 is the full dataset, I2 and I3 are the two halves, and I4 to I7 are the 4 quarters of the data, so of the tasks. The calculation time starts with some minutes for a quarter of the data with 100 generations, up to 260 minutes for the full data set with 500 generations. So this means running all calculations one time sums up to around 1,800 minutes or 30 hours of processing time. So let us check the results. For the results, these calculations were run 10 times, and here the values with the standard deviations are reported. On the vertical axis, the solution quality is displayed. The goal was here to minimize the solution quality. On the horizontal axis, we can see the used encoding and the amount of generations for the genetic algorithm. So the int stands for the integer encoding.
Sorry, just 1-2 minutes to go to the conclusions.
Yeah. Okay. So here we have the encoding and the amount of generations. This means for the halves and the quarters are summed up here. So this means that for the full dataset I1, the cobots are positioned once before the production starts. For the halves, the cobots are positioned twice before each half starts producing, and for the aggregated quarters, cobots are positioned 4 times before each quarter starts. What can be seen here is that the real encoding delivers better results in most cases, especially after 200 and 500 generations. And to conclude, we also wanted to compare the results with cobots with results without cobots. So we also run all calculations without cobots, and we used, for the cobots we had 5, so for the runs with cobots we have 5 cobots on the 50 workstations, and the amount of generations of the genetic algorithm influenced the improvement that cobots yielded in planning. So after 100 generation, we had an improvement of 13% with cobots. After 200 generations, we had an improvement of 15%, and after 500 generations, we had an improvement of 18.5%. So this means by deploying 5 cobots in critical stations in the manufacturing process with 50 workstations, an overall target function improvement of 18.5% could be reached. So thank you. And are there any questions?
Thank you very much, Alexander, for your speech. I can see already a question from Professor Michael Affenzeller, please.
Okay.
Okay. I have a question concerning the real-valued flavor of genetic algorithm. Have you also tried out combinations of operators? So not say I do this crossover and this mutation, but also a combined usage of operators. We have experienced that, especially in combination with offspring selection, this often brings some benefits in terms of qualitative performance. Have you tried out such strategies?
I did not try them out yet, but this would be an interesting topic for like a follow-up paper, so that we compare the different operators. And also, for example, if we use multiple of these operators, so like multiple crossover and multiple mutators. So,
Yeah.
So I think this would be really interesting, but I did not try it out yet for this paper.
Okay. Yeah, but could be. But if you do so, I would suggest you to use offspring selection, not in order to get all results into the next generation.
Okay. Yeah.
Okay. Thanks.
Thank you. Any other question from the audience? So seems that no one has other questions. So thank you, Alexander, again.
Thank you.
And we can move to the third speaker, who is Letizia Tebaldi.
Yes, here I am.
Who is going to talk about a bibliometric analysis on collaborative robots in logistics 4.0 environments.
Okay, can you hear me and can you see the presentation?
Yeah, perfect.
Okay, so I can start. Good morning, everyone. I'm Letizia Tebaldi, second-year PhD student in industrial engineering at the Department of Engineering and Architecture of the University of Parma. And during this brief presentation, I will illustrate the results from a bibliometric analysis carried out on exactly 64 papers, which deal with the topic of collaborative robots within logistics systems, as you can understand from the title. And the topic, the context is clearly that of logistics 4.0, a term which was coined since the well-known Fourth Industrial Revolution also affected the logistics field. And more in general, the aim of the well-known Fourth Industrial Revolution is that of digitalize the manufacturing field through the connection between physical and digital systems, and thanks to prompt analysis based on big data, which are nowadays available. And specifically within the logistic field, the main application, as you can read in this slide, are autonomous robots and vehicles, tools for keeping control of the inventory or for improving the information flow, and real-time big data analytics of vehicles, or also strategies for optimally routing transport. And from these technologies, it is expected a saving in cost equal to 34.2% and additional revenues of 33.4% concerning the logistics activities. As I said at the beginning, the topic is specifically on collaborative robots, alias cobots, which is a term which originates from the union of two English words, that is to say robot and collaboration. And despite its first mention goes back to 1999, they became popular around 15 years later. Here you can read the definition of cobots provided by the ISO organization, and which defines cobots as robots designed for direct interaction with a human within a defined collaborative workspace. So they have no more to be kept away in a caged area, but rather they collaborate with humans in the same spaces. The main applications within logistics are related to pick and place activities or palletizing and assembling, or they can also be applied on automated guided vehicles. The reason why we have chosen this specific technologies is that publications related to this topic start being numerous, and we wanted to inspect some descriptive parameters and metrics. In order to define the sample of paper to be analyzed, we have launched different queries on Scopus database in February of this year. Here you can see the list of the keywords, all dealing, of course, with cobots and synonyms and logistics. And after having excluded the redundancies and off-topic papers, the result is 64 papers analyzed overall. We used two different software for carrying out the analysis, that is to say Microsoft Excel, thanks to which we investigated the year of publication, so the evolution over time, journals and conference proceedings, citations, keywords, author and geography analysis. And then we also use VOS Viewer, which is a common software developed for constructing and visualizing bibliometric networks, and thanks to it we deepen the citations and the co-authorship relationship. From this slide, I start with the introduction with the real results. So the first descriptive parameter is the evolution over time. In this histogram, you can see that the first paper dates back to 2001, and since 2015, production is rather lacking. In fact, only around 16% of the sample belong to this period. The remaining 84 belongs to the last 5 years. It is worth mentioning year 2019, in which 33 papers were published. And finally, note that for this year, we have just considered January and February, and a total of 9 papers was recorded. So it is expected by the end of the year a significant increase in publication and also in the future. Instead, on this histogram on the right, you can see the type of document related to publication. Blue color refers to journal articles, which are 33, red to conference, which are 30, and finally green in 2016, it is the only literature review found which deals with the state of art of literature related to collaborative robots. The journal and conferences analysis follows, and we found a total of 25 scientific journals and 20 international conferences or conference proceeding journals, and most of them present only one paper, exception made for some conferences. And it is worth mentioning the IEEE International Conference on Emerging Technologies and Factory Automation, which took place last year in Spain, and it contributed with 6 papers. In fact, the topic of factory automation is perfectly in line with that of collaborative robots, of course. Then the citation analysis follows, and in this slide you can see, and in the following slide you can see the most cited paper. Let's say we consider it a paper who reached more than 20 citations, and they all belong to the first period of production. In fact, the oldest is in 2011, exception made for the most cited paper, who is from Barreto and co-authors, which was published in year 2017, and it already got 90 citations, which is a good result because it was published 3 years ago, and it is an overview on Industry 4.0 implications in logistics, including, of course, collaborative robots. Overall, we found 411 citations. Then we analyzed the keyword frequencies after having, of course, adjusted acronyms and spelling words, and we have also removed the keywords used for the queries because they would alter the result. We found 185 keywords overall. In this slide, you can read the ones that got more than 5 mentioning, and in brackets the number of papers in which they were mentioned. And the first is Industry 4.0, which confirms that these technologies are treated as being brought from the fourth industrial revolution, and Internet of Things, which demonstrate that the joint use of cobots and IoT platforms allows for programming cobots and to collect and visualize all the data which are scanned from the collaborative robots. Then supply chain follows. Okay, this of course the topic investigated is that of the field of logistics, and this result does not surprise. It is worth mentioning that all the mention which received by the keyword supply chain are all in 2019. And this actually could be to the fact that at first publications were more related to cobots from a technological point of view, and then the attention was shifted to the real implementation of cobots within the context, the industrial context. And then we find intelligent systems and smart systems, which can be seen as attributes that are associated to collaborative robots. Then we analyzed the authors who wrote the papers. We found a total of 219 authors, and because all the papers were written from more than one author, and all the authors collaborated to just one paper, except for 2 professors, who are Professor Leonard Barolli from Japan, who wrote 2 papers, both presenting a peer-to-peer platform supporting distributed and collaborative systems. And one of these papers got 66 citations, and it was listed in the table of the most cited paper. And the other name that result is that of Vera Hammel, who is a mechanical engineering from Germany. And she wrote 2 papers, and one is with the development of a solution in order to facilitate operators in programming cobots. And the second paper instead presents a collaborative Tagger train systems combined to other manual and semi-automated conveyor systems, which is implemented in order to reach self-organization and autonomous control of intralogistic systems. The last aspect investigated thanks to Microsoft Excel is the geographical distribution, and just note that almost half of the sample was produced by the first 3 countries you can see in this histogram, which are Germany, and it does not surprise since Industry 4.0 was born in this country, China and USA. So the first analyses are that are obtained thanks to both viewer, and we could further explore and deepen the citation analysis and see different visualizations of results and the links to other different aspects. So in this slide, you can see the network visualization, and the size of each sphere that you can see each sphere is associated to a publication, which is represented by the group of the authors, and the size depends on the absolute number of citations, and it confirms the result achieved from the analysis made under Microsoft Excel, because bigger sphere corresponds to the papers, to the group of authors whose papers got more citations. And instead, this figure instead is similar to the previous one, but in this case it is the density visualization, and the shades occur in the presence of most cited paper, and the color refers to the year. And again, this time we can confirm the results of the table that I showed you previously. Okay, probably for you these are just name of authors, but anyway, trust me, because results are confirmed. And then if we want instead to analyze the internal citations, if the citation got by the paper of the sample are within the paper of the sample, we move the weight from the absolute number of citations to the links between cited paper, and this is an extract of the resulting visualization. Again, this time stands out Barreto, which was the paper who got the highest number of citations. And so this means that among the 90 citations which it got, some of them are within the sample of the 64 papers under investigation in this work. And this not happens for the remaining papers because the name resulting from this visualization are different. But anyways, as I have already said, these are just named for you. This is just for showing you the interesting visualization and analysis which can be achieved thanks to this specific software. Then the last aspect investigated is the co-authorship. And the only interesting result is related to the group numerousness. And in this slide, you can see the visualization which is obtained, and each sphere corresponds to an author, and the shades to the links to other authors. And it is clear that some groups are bigger than than other. And since the color refers to the year in which they worked, this fact suggests that most of these numerous groups have worked over the last 2 years. So this means that not only the attention, COBOTs are receiving attention, but also the professors, academics and practitioners who are working on this topic are increasing. So this was the last aspect that we have investigating. And for concluding, I have just briefly present some key results from a bibliometric analysis that we have carried out on 64 papers, whose topic is on collaborative robots applied to logistics system. Overall, we can assess that the topic is spreading, and we recorded an upward trend over time of publications, and different contributions are coming from different countries, and also the working groups are becoming larger in terms of number of components. And this also confirmed that the logistics field is one of the most promising, as also demonstrated from the keywords analysis. And it is expected in the years that will follow further increase, as we believe that improvements related to this new technology are still almost revolutionary than evolutionary. And it is in plan for the future, a literature review dealing this time with the real content of the papers, and this was just a preliminary works. And of course, all the paper of this session will be included, as the topic, of course, is in line. And I have finished. Thank you for the attention.
Thank you very much, Letizia, for your promising work. Are there any questions from the audience? I actually have a question, because you mentioned that in 2019 there was a very sharp increase in the number of papers publishing in the area of cobots and logistics 4.0. So if I remember well, there were around 33 papers 33, against
yes, almost
35. Yeah, against 3-5 papers in the other year. So can you better explain this? Was it because of a special issue or a conference track on the specific topic?
Yes, as I said, last year the IEEE conference on automation of factory took place in Spain, and it got 6 papers. And also this can actually be due to the fact that the process of peer reviewing requires a lot of time. So probably the published paper in 2019 were also the results from studies which were carried out previously. So the industry 4.0 and the topic starts spreading from, as we read, from 2015 around. And so I think that for ER is a reasonable time to get the most of the production of papers concentrated in 2019.
Okay. So you are expecting to have similar numbers also in 2020.
Yeah, we know. Yes. The only problem related to probably to the future and to real implementation of cobots is probably the pandemic situation that is now affected the world, because probably there are a lot of companies who are having problems. So probably these are investments which was attention, and the attention maybe shift to other investments. I don't know if you understand.
Yeah.
I was talking about the implementations of collaborative robots.
Okay, thank you very much again for your nice speech. And we can move to the last speaker today in this session, who is Yaxu Niu. And Yaxu is going to present the work entitled Human Aspects in Collaborative Order Picking, letting robotic agents learn about human discomfort. Please, Yaxu.
Yeah, I need to share my screen first.
Yeah.
Okay, can anybody see the screen and hear the view? Yeah, okay, perfect. Thanks, Antonio, and hello everyone, welcome to my slides. I'd like to talk about human-robot collaboration in warehouses. Everybody knows in Amazon warehouses, there are human and robotic workers collaborating. For instance, order picking. Here can take that as an example. And there are a lot of models for order picking and collaborating aspect. What we don't find there is a model where a robot can actually learn human discomfort. So in this paper, we have developed a multi-agent reinforcement learning approach to tackle this issue and have some findings. I'm Yaxu Niu, a visiting PhD student supported by CSC and now studying at the Delft University of Technology. My co-authors are Assistant Professor Friedrich Schroth and the Professor Rudolf. I will introduce our work from the following 5 parts, and the first part is the background. Our interested system is a robotic mobile fulfillment system, which is a new type of automated storage and parts-to-picker order picking system, particularly suited for the e-commerce distribution center. It can be observed from the picture that the system is mainly composed of robots, the shelves pocketed in the storage areas, and pickers working at workstations. In the order fulfillment processes, robots can move under the shelves and directly reach the targeted shelf. Then the robot lifts the shelf and transports its along aisles and cross aisles to the workstations and waits for the picker to pick up products from the shelf. Finally, the robot returns the shelf to the storage areas and waits for the next task. Usually, the system layout can be illustrated as the left picture, and this kind of system can handle strong demand fluctuations and large assortment of small productions in e-commerce. Compared with the picker-to-part order picking system, the robot can greatly reduce the travel distance of pickers, thereby improving the efficiency of the system. And it's easier to add or remove shifts or robots. It means that it's easier to deploy. Furthermore, extensive human-robot collaboration exists. Current literature mainly focuses on the layout strategy and the operational strategy to improve the system efficiency. So we are going to have a question. How efficient is this kind of system? According to the critical literature that introducing the system, each picker can complete 600 order lines per hour. This means that in practice, pickers have to face a lot of repetitive work, and under this kind of high-intensity workload, human pickers often become the bottleneck of the system efficiency. So it is important to consider human factors such as the fatigue, the discomfort when designing or optimizing the system. Recently, some literature also pointed out that neglecting human factors often lead to unrealistic planning outcomes or work schedules that may even be harmful to workers employed in the system. However, there are a few studies in the literature considering human factors. An overview of the research concerning the decision problems in the system can be found in the table. It's become apparent that most related work focuses on the strategy, tactical, and operational level decision making. Only though et al. Consider the influence of human pickers' handling speed. These factors empowered us to consider human factors into the operational strategy to achieve a human-friendly policy. We mentioned earlier that pickers will face a lot of repetitive work because of the difference in pickers' processing speed. More efficient pickers may be assigned more order tasks, which result in different workload. And moreover, different workload may lead to different level of discomfort among pickers. It's unreasonable to continue to assign order tasks when the picker feels discomfort, whereas other pickers may have nothing to do. So, as shown in the picture, the robot should not only consider the efficiency, but also consider the level of discomfort of the pickers, and to avoid excessive discomfort difference between the workers. We aim to develop a decision support approach that enables robots to learn about human discomfort next to minimum processing time when working with human pickers. Firstly, to simplify the system, we made some assumptions about the three elements. And the first is the robot. Robots are always busy in a fully observable environment and can independently execute tasks with constant speed. The shift has three layers, and a first come, first served policy is used at the workstation. The shift waiting time is constant, and the picker can complete single line order at a constant speed, but the speed is different from each other. The state of the system at time step t can be represented by the robot state vector, the order information vector, and the workstation information vector. Based on the robot state vector and each order task assignment decision, the robot, and the time required to complete all the assigned orders to the robot can be estimated by this formula, which can be defined as the individual total make spin time. Furthermore, the maximum time of the individual total make spin time determines the total make spin time. From the perspective of system efficiency, assignment policy is required to minimize the individual total make spin time for each robot without sacrificing other robots' performance, and to minimize the total make spin time. To estimate the level of pickers' discomfort caused by each product, the following formula is used, which is the joint work result by Lacko and De Coster. In the formula, products on the different layers of the shape also will cause different levels of discomfort. And the discomfort will be also generated by the products with high mass, high and medium and high volume, medium and high quantity. The term IND allows for the possible interaction effects with picking at different layers. Dummy variables indicating individual characteristics, and it also indicates that personal characteristics have little impact on pickers' discomfort in the studied two real warehouses. So finally, the discomfort formula can be simplified as this equation. According to the discomfort estimation formula, order information vector and the work information vector can be defined respectively. Based on the state of the system at time step t, each robot can select one of the workstations to complete the task or not make a decision because it's performing a task. After the decision, each robot will receive a penalty regarding time cost and discomfort. And the adult robot the adult robot doesn't make assignment decisions, or the robot make assignment decisions without completing the current order task and will receive a significant penalty. And the final objective is to let robotic agent efficiently learn to consider human discomfort next to minimum processing time. To achieve this objective, Q-learning, the basic algorithm in reinforcement learning, is used to solve the problem. The value of an assignment decision of a robot at a state is evaluated by a Q value, which represents an estimation of the discounted sum of the future penalty. Q value can be estimated by this formula, and alpha is the learning rate that determine what percentage of the old value, Q value will be fixed by the newly acquired difference between the new value and the old value. Gamma is the discounted factor that determines the importance of the future reward after getting the value function, and the optimal action for each state is given by this formula. However, solving the optimal policy has to do with the curse of dimensionality problems and caused by enumerating all the robot state and order and workstation information. To solve this problem, the neural network is used to approximate the value function, and the theta is the neural network weight. And the neural network is trained by minimizing the loss function. The epsilon greedy policy is used to choose actions at each time step, and the explosion rate is calculated by this formula. The pseudocode is used to clarify the learning process. In each episode, the behavior is selected for each robot at each time step. Then robot observes the penalty and enters the next state. The robot will save the experience state transitions for later neural network training. We test the method in a system, and the system's parameters are shown in the table. The figures are the demonstrations of the convergence of the algorithm, indicating the total max spin time and the total discomfort level of each workstation. We compiled our method with 4 commonly used assignment policy in terms of total max spin time and discomfort difference. Sorry. The optimal assignment policy is obtained by enumerating all possible assignment decisions and find the minimum max spin time among this policy. It can be seen that the proposed method has the smallest discomfort difference, and its efficiency is not much different from the optimal strategy. In our work, human-robot collaboration in the order picking system is mainly considered, and human pickers' discomfort level has hardly been considered in collaborative order picking, as common in robotic mobile fulfillment system. To fill the gap, we propose a multi-agent reinforcement learning approach for a human-oriented robot assignment problem, and the result confirmed that the developed approach can let the robotic agent beware of human pickers' discomfort. In the future, we'd like to integrate human sensor data, such as the heart rate and cortisol from the wearable device, and integrate the fatigue, working efficiency, and other factors encountered by pickers in the system. We will also introduce a coordination mechanism in the multi-agent reinforcement learning and extend the method to the large-scale systems. Finally, the method will be applied to the actual systems. That's all. Thanks, Shu, and thank you as well. I'll be happy if I receive some questions.
Thank you very much, Yaxu. Any question? Yeah, Andreas.
I have a question regarding the discomfort level. Is this, you mentioned a formula that was published in a paper. Did you find other works also that consider this? I think is this agreement that the discomfort is a kind of a sum of some of these factors, or are there other models maybe from the psychology domain?
Yeah. The discomfort level can be estimated by this formula, of course, and also can be by the data-driven methods. And in the Laco and the Coster's work, they model the discomfort as a linear model, and using the warehouse data to estimate the linear coefficients and have the discomfort level equations. And all the main influenced factors was considered, like the layer and the mass and volumes, the quantity, and these factors are regarded as the main factors that have an influence on the picker's discomfort, and other factors has little influence on the discomfort level was represented by epsilon. This is epsilon, so this formula can be estimated the discomfort.
And this is the only work that kind of describes such a formula. There's no other formula, or at least none that you know of.
Yeah. It's not the only way to estimate. This formula is just used to one method to estimate the discomfort, and this method was proposed by the paper, and I used this work results.
Mm-hmm. Okay, thank you.
Okay, thank you for your question.
Thank you, Andreas. I can see also another question from Fabio. Fabio, please.
Yes, thank you so much. I am here, Fabio from Unibas, University of Basilicata, Italy. Thank you so much for your presentation. I found the presentation really interesting. My question is still on the same as before, this formulation, discomfort estimation, and maybe on the conclusion that you present with reference to the further steps. The question is about, do you think that in the discomfort level need to be included something related with the human anthropometry, maybe something like ergonomy inside the discomfort estimation? Do you think that ergonomy need to be included inside? Because I suppose that some factor that you mentioned in conclusion, like for example fatigue, could be influenced by the ergonomy, by the anthropometry of human at work.
Yeah, I think your question is a trade-off between the economic and the human discomfort, right? And yeah, in our work, we use multi-agent reinforcement learning, and the reward function was used to guide the agent to learn the objective. And in the reward function, we already defined the time cost penalty and the discomfort discomfort level penalty. So the agent can learn the both objective and find the trade-off between these two factors, two objectives. And as you said, the human maybe feel discomfort or fatigue, and also you need to consider the economic. Maybe the human pickers feels fatigue, and the performance may be decreased, and then we need the pickers need to have a rest or assign less other task to the robot, and this part this planning was thought in our next step, and considering the considering to develop a method to develop a policy that let the robot to learn the decision making depend on the human picker's performance.
Okay, thank you so much.
Okay, yeah. Thanks for your question.
Maybe Frederick has also another question.
I just want to clarify because I'm a co-author and
okay.
The point was, I think the questions were directed if the DISCOMFORT needs to be modeled in an individual fashion, and in the first step that we used the formula by de Coster, it was not an individual way, but now that we're going more to sensor data, we can really take individual measures from the humans into account in the next step of the research. I think that was maybe important to add.
Thank you very much, Frederick, for your additional insights. I don't know if Fabio wants to
say. Thank you for your insight. I think that I understood your point. I suppose that in the future work, something related with the probabilistics of time need to be included as well, because your scheduling approach need to consider also that point that the time is not constant but will change according to the learning in this case, and eventually to the other factor that you want to include.
Yes. Thank you.
Okay, if there are no more questions, I guess we can close this session. So I thank you again, Yaxu, for the speech, all the other speakers and the attendees for joining this session. And see you this afternoon. Thank you, everybody. Bye.
Bye. Thank you. Bye.
Thank you. Bye.